Hi guys, so chapter 6, we took that chapter test before the break. It was over 6.1 through 6.5. We didn't do 6.4, but that's not the key part to it. Because the only thing we have left with chapter 6 that we're going to cover is solving. Because we've done everything but solve quadratic and exponential equations. And we saved it, and I saved it till after the break, mainly because we just didn't have enough time to cover it and test before the break, and I didn't want to split that up and try to test over everything after spring break, after a week off. So we split it up. And what we're covering today is the first part of solving. Now, they call this the property of equality for exponential equations. It's also can be called one-to-one property. If b is a positive real number other than 1, then b to the x is equal to b to the y if and only if x is equal to y. And really what that is saying is if we have an exponential equation and the base on either side is the same, the exponents have to be equal. So the only way that 5 to the 3 minus 2x is equal to 5 to the negative x is if 3 minus 2x is equal to negative x. The only way that this is equivalent is if the exponents are the same, if the exponents have the same value. So for us here, 5 to the 3 minus 2x equals 5 to the negative x, whenever 3 minus 2x is equal to negative x. So, questions on this here before we move on to the next step? Now we just need to solve for the value of x. What can we do first? I would add 2x. Because the constant term, the number without a variable, is already on one side. We need to get the x's on the same side. So we can add 2x to both sides. Because on the left-hand side, we'd be left with 3, because our negative 2x plus 2x would be 0. Our negative x plus 2x is, so it's telling us x is equal to 3. Questions on this here? You're good. That's it. Because we can check and make sure, because we can plug it into the calculator. 5 to the 3 minus 2 times 3 gives us 1 over 125, and 5 to the negative 3 is also 1 over 125. So the value of x is indeed equal to 3. And that's it. Now the first few of these here work out kind of nicely, but this process still holds true. Now if we look at the next one, 6 to the negative 2a is equal to 6 to the 2 minus 3a. Since the bases are the same, the exponents have to be equal. So our negative 2a is equal to 2 minus 3a. Questions on this here? What do we need to do first? So we can add 3a to both sides. Because that will get our variables on the same side. Negative 2a plus 3a is a. Negative 3a plus 3a cancel out, telling us that a is 2. Questions on these first two here? Are you ready for the next one? Three to the 2a is equal to 3 to the negative a. Since the bases are the same, the exponents have to be equal. So our 2a has to equal negative a. For whatever value of a that makes this statement true, we'll make the two equations be equal. We can't quite divide it yet. We'd want to divide it after we get all the variables on the same side. So what can we do first? Add what? Well, we would just add a. Because our negative a plus a is 0. 2a plus a is 3a. Now we would by 3. We would divide both sides by 3, telling us a is 0. And that's it. Because once we get the bases, 1 on each side, and they are the same, we can set the exponents equal to each other and solve. Now, even with this here, if we check this one, 3 to the 2 times 0 is equal to 3 to the negative 0. So that'd be 3 to the 0 is equal to 3 to the 0. And anything to the 0 power is 1, so it'll tell us 1 is equal to 1. And that's it. Questions on this here? We can look at the next one. 2 to the 2x plus 2 is equal to 2 to the 3x. The bases are both the same. So our exponents have to be equal. Our 2x plus 2 has to be equal to 3x. So what can we do first? We can get the variables on the same side, so we can subtract 2x from both sides. Because 2x minus 2x is 0, leaving us with 2. 3x minus 2x is x. And since x is by itself, x is equal to 2. Questions on this here? I mean, we could have more steps where we're adding, subtracting, but it's just solving at this point. It's just like with this next one. Since the bases are the same, we have one base on either side, we can set the exponents equal to each other, yes? Right, we don't have one base on either side. One of the sides we have 2, yes? If we multiply like bases, we can add the exponents. Because we do need it to be a single base on either side. So here, 6 to the 3m times 6 to the negative m, we can rewrite it as a single term. Because when we multiply like bases, we can simplify it to 1 and add the exponents. Because when we multiply like bases, we add the exponents. Because we need it as a single term. Because if it's not a single term, our one-to-one property doesn't work. So you're good. Now the left-hand side, our 6 to the 3m plus negative m would be 6 to the 2m. Any other questions on this here? Now, since the bases are the same, it means the exponents have to be equal. Because the only way 6 to the 2m is equal to 6 to the negative 2m is if our 2m is equal to negative 2m. What would we need to do next? I would add 2m first. Because it would be possible to divide by 2, but we would still end up having to move everything to the same side. Because we want to get all the variables together first in our multi-step equations before we divide. Because our negative 2m plus 2m would be 0. 2m plus 2m is 4m. So then we would indeed divide by 4, telling us that m is 0. Questions on this here? Questions on anything we've done so far? We good with all these so far? Well, number 13, we have 4 to the negative 2x times 4 to the x. Whenever we multiply like bases, we can add the exponents. So that would give us 4 to the negative 2x plus x. Questions on this so far? Now, since the bases are the same, we can set the exponents equal to each other. Yes? Are the bases the same? Because on the left-hand side, our base is 4. On the right-hand side, the number is 64. So if we're going to solve it this way, we really need to rewrite 64 as 4 to a power. Yes? 4 to what power is 64? Because 4 to the fourth is, so 4 to the third. Because we didn't pick 4 just out of the blue, but because the other side, the base was up 4, so if we can rewrite 64 as 4 to a power, we're going to use it. If not, we'd have to look for another number that we would rewrite both as. Now our negative 2x plus x is negative x. Now are the bases the same?
Yeah.
Yeah. And it's also telling us that negative x is equal to 3. Since the bases are the same, the exponents have to be equal. That's the only way that these two equations can be equal. And the last thing we need to do is we can divide both sides by negative 1. We can multiply by negative 1. But we need to get our x to be positive instead of negative. And when we do this, it turns the 3 from positive to negative. So here x is negative 3. Questions on these so far? We feel good with these so far. Because really the whole goal is to get the bases to be the same. Because once we have the bases the same, we can set the exponents equal to each other. Now the next one we have is 100 to the x is equal to 1/10 to the x minus 3. Now we need to get both of these bases to be the same. And the first thing I would do is move that 10 from the bottom of the fraction to the top, because it's going to be easier to work with non-fractional numbers. Now the only way we can get the 10 from the bottom of the fraction to the top is if we change the exponent attached to it from being positive to negative or negative to positive. Because if we move a number from the bottom of the fraction to the top, its exponent goes from positive to negative or negative to positive. Now 10 did not have an exponent written specifically with it. We do have 1, so it would turn it to negative 1. Questions on this here? Now, is there a way that we can rewrite 100 as 10 to a power? 2. 10 squared would indeed be 100. Questions on what we've done so far? One of the properties of exponents is that powers of powers multiply. So here 10 to the 2 to the x, our 2 and x would multiply together, giving us 2x. So we'd have 10 to the 2x. On our other side, we'd still have 10 as our base, but our negative 1 and x minus 3 would multiply out. So we have negative 1 times x, which would be, indeed, and our negative 1 times negative 3 would be plus 3. So we'd have 2x, or 10 to the 2x is equal to 10 to the negative x plus 3. Questions on how we got to this here? We good with this here so far? Now, since the bases are the same, we can set the exponents equal to each other. Questions on any of this so far? What would we do next?
X.
I would agree. Because we do have variables on both sides of the equation, so we need to get them together, and the numbers are constant terms by themselves. So our 2x plus x is 3x. Our negative x plus x would be 0. So we get 3x equals 3. And then we would by 3. So x is equal to 1. As if we check this, 100 to the first power is indeed 100. Now the other side, 1 over 10 to the x minus 3, so 1 minus 3 is also 100. So they do give us the same answer. Questions on that one there? We ready for the next one? Well, just like the last one, we can move that 9 from the bottom of the fraction to the top. And to do that, we have to change the exponent from positive to negative, and it ends up being negative 1. Now the question is, can we rewrite 81 as 9 to a power? 9 squared, yes. Now, if 9 had not worked, we'd have to find another number. 3 would also work. But we want to get those bases to be the same for us to be able to use this one-to-one property. Now, because of our exponent properties, 9 to the second power to the x is the same as 9 to the 2x. Our 9 to the negative 1 to the x plus 3, we'd have to distribute the negative 1 to both, giving us negative x minus 3. Questions on this here? Since the bases are the same, the exponents have to be equal. Questions on this here? Questions on any of this so far? What would we do first? We can add x. Our 2x plus x is 3x. Negative x plus x is 0, leaving us with negative 3. And lastly, we would divide by 3. So x is negative 1. That's it. Questions on this here? So the whole goal for these problems is to get the bases to be the same, because once the bases are the same, we can set the exponents equal to each other and solve. Questions on this here? Very good. We good with this here? We have one more like it. 3 to the 1 minus 2x is equal to 243. Well, it would be nice if we were able to rewrite 243 as 3 to a power. Because if we could, the bases would be the same, and we could set the exponents equal to each other. 3 to what power is 243? Take a guess. So e to the fifth power is 243.
Well, I said that earlier.
So 243 is 3 to the fifth. So we have this here. Now the bases are the same, yes? And if the bases are the same, the exponents have to be equal for this equation to work. What can we do first? Yeah. Because up to this point, we've been moving the variable, adding the variable or subtracting the variable from both sides. But here, this first one where we only had the variable show up once, we need to get the numbers by themselves too. So we can subtract 1, and our 1 minus 1 simplifies out, telling us negative 2x is equal to 4. And we divide both sides by negative 2, telling us x is equal to negative 2. And that's it. Now, solving exponential equations are kind of nice because there are no restrictions to it. The only time that it doesn't work is if x is an imaginary number. Then there's not going to be a solution. But there are no extraneous solutions to it. It just ends up being non-real numbers. The other thing we're covering today is our one-to-one property with logarithms. If b, x, and y are positive real numbers, so b, x, and y cannot be 0 or negatives, with b different from 1, then log base b of x equals log base b of y if and only if x is equal to y. So if the logarithms are the same, and they're equal to each other, one on either side, then what's inside the logarithms has to be equal. Apparently I'm going to throw the pen. So if we look at this here, the natural log of 4x minus 7 is equal to the natural log of x plus 5. Well, the natural logs match up, which tells us that 4x minus 7 has to equal x plus 5. If we have one log on either side of the equation and it's the same log, what's inside of each log has to be equal. So here 4x minus 7 has to equal x plus 5. Now we just need to solve for x. So what can we do first? Yeah, we can add 7. It's not the only thing we could have done. We just had to pick one and go with it. Because we could have also subtracted 5 from both sides. We could have subtracted x, or we could have subtracted 4x. We just had to pick one of them to do first. And since we added 7 to both sides, it kind of restricts us in what we can do next, because our next one would be 2 minus x, because we want to get the variables together, our constant terms together. So 4x minus x is 3x is equal to 12. And lastly, we would divide by 3. So x is equal to 4. And that's it. And if we wanted to, we could plug it back in. ln of 4 times 4 minus 7. That would be ln of 16 minus 7, which is the natural log of 9. The other side, ln of 4 plus 5 is natural log of 9. And indeed, the natural log of 9 is equal to the natural log of 9. And what's inside our log is not 0 or negative. This spot here is not 0 or negative, so that works. So our solution for this is x is equal to 4. I was just checking it. We could have also done that in a calculator, ln of 4 times 4 minus 7, and found its value, and saw what ln of 4 plus 5's value is, and they will give us the same decimal number. What would we do for the next one?
7x minus 4 is equal to 2x plus 1.
Yes. Since the logs are the same and we have 1 on either side, 7x minus 4 is equal to 2x plus 11. Yes, we can add 4 to both sides. So 7x is equal to 2x plus 15. Yes, and we would indeed subtract 2x from both sides, telling us 5x is equal to 15. Then we would divide by 5. Yes. That's it. Questions on this here? Now, I'm about to have you recall something from before the break. What would e to the ln of 4x minus 7 be? E to the ln of 4x minus 7. What would the e and ln do?
4x minus 7x.
If I do it to one side, I have to do it to the. So it's telling us 4x minus 7 is equal to x plus 5. That's why this works, because we're really just putting both sides to the base of the logarithm, which in this case, both of these are e. Then it would do the same thing. That's why we have this one-to-one property. Let's look at this one here. We want to solve the natural log of 5x plus 2 is equal to the natural log of x plus 10. What would we do first?
Oh, 5x plus 2.
5x plus 2 is equal to x plus 10. So since the logs are the same, we can set what's inside of them equal.
And subtract 2.
We can subtract 2. Minus 5x is equal to x plus 8.
Subtract 8. Or wait, now subtract
X. We can subtract x from both sides, telling us 4x is equal to 8. Then divide both sides by 4.
2.
X is equal to 2. That's it. Questions on these here? Do we like these for the most part? Our next one, log of 5x equals log of 2x plus 9. The logs are the same, yes? So that tells us what? That 5x is equal to 2x plus 9. We would indeed minus 2x. 5x minus 2x is? Because our 2x minus 2x would be 0, leaving us with 9. And last but not least, we would divide by 3, telling us x is 3. And that's it. Questions on this here? Questions on anything we've done so far? Because I know I think yours has x instead of v. That's fine. They are the same. It's just a variable. But if we look at this next one, log base 12 of x squared plus 35 is equal to log base 12 of negative 12x minus 1. are the logs the same? Doesn't matter that it's log base 12, but because they are both the same log, what's inside is going to be equal. Because if we want to do like we did for E, I could put both sides to the base of 12, because 12 to the log base 12 would cancel. So that simplifies out, telling us that x squared plus 35 is equal to negative 12x minus 1. Now, since this is a quadratic, this is the first one we've had as a quadratic all day, we need to get it equal to 0. So it doesn't matter what we move first. I'm going to move the 12x. So I'm going to add 12x to both sides, which will tell us that we have x squared. 12x plus 35 is equal to negative 1. And then we would indeed add 1 to both sides. Telling us that we have x squared plus 12x plus 36 is equal to 0. Questions on this here? Now, since we do have a quadratic, we can solve this by graphing, factoring, or the quadratic formula. Now, if we wanted to graph it, well, incidentally, I already have it typed in. X squared plus 12x plus 36. Whenever we graph it, we're looking for where it crosses the x-axis. We're looking for what value of x makes the y value be 0. And if we look at the table, the x value that makes the y value be 0 is negative 6. So here the solution is x is equal to negative 6. And that's it. Now we could plug it back in and check it if we wanted to, because we'd have log base 12 of negative 6 squared plus 35. And we want to see if this is equal to log base 12 of negative 12 times negative 6 minus 1. On the left-hand side, our negative 6 squared is 36 plus 35. On the right-hand side, we have negative 12 times negative 6, which is going to be positive 72 minus 1. And it would tell us that log base of the 71 is indeed equal to log base 12 of 71. It does work. Questions on this here? And that's it. And something is, I don't think, agreeing with me. But that's it. That's all we're doing today. 5 through 8, 11, 12, 21 through 20 through 20.